Next is a presentation from Jamie Smith, who is the Director of Automotive Design and Research for National Instruments, with his presentation on advances in autonomous vehicle tests. He's already there, so I think, Jamie, you should be able to be audible now. 1 second. Jamie, can you hear me?
I can.
Perfect.
I can. Should I leave my video off, or do you want my video on?
As you like, as you like. I mean, maybe for the Q&A session in the end, but I think more important is the screen sharing. That should be able now.
Okay, I will do it now. Okay. Let me know when you can see the presentation.
We can see the presentation now. Could you switch it? Perfect. All right,
Yep.
You're set to go.
Perfect. All right, everyone. Thank you for attending Tech.AD. I'm really excited to have the opportunity to present to everyone today. My name is Jamie Smith. I work at NI, and I focus on research and design of autonomous vehicles, as well as the testing of the components in the vehicles themselves. One big piece of information before I dive in is who we are. So many of the people that are in attendance today probably know National Instruments and have had experience with our equipment. But for those of you who aren't familiar with us, we're roughly a $1.4 billion company that serves the global market and provides testing and measurement equipment, focusing on a wide range of industries, where one of the most important industries is automotive. And in the last 2 weeks, we actually changed our company name. So National Instruments is now NI. So we have legally changed our name as we've grown over the last 45 years into a global company. The term National Instruments understates who we are and what we do. So we've changed our name to NI. So now that I have that aside, let's dive into the talk. Okay, so I think everyone that's attending this conference is aware of what the contemporary vehicle looks like, a vehicle that's striving to be an autonomous vehicle. It's a collection of advanced compute, communication, and positioning, similar to V2X and GNSS or GPS, as well as a wide range of sensors. Multiple LiDARs, perhaps, multiple radars, many cameras, perhaps ultrasound, and then maybe other sensors beyond the IMU on the car. So lots of sensors, lots of compute. And adding these capabilities to the vehicles is really paying off. We're seeing a lot of decrease in accidents and increased safety, and cars that have ADAS features. So reduction in rear collisions and sideswipe collisions has been tracked and proven. So that's really good news for those of us that are working towards autonomy and the safety that will deliver to the marketplace. And while radar has been in cars for quite some time now, radar technology is not standing still, right? Radar technology continues to evolve. And the primary way it's changing is the bandwidth for the radar sensor is going up, which increases the resolution of the radar sensor. And to illustrate that point, here's a view of what a 24 gigahertz sensor, which has pretty narrow bandwidth. It's centered at 24 gigahertz, but has about 200 megahertz of bandwidth, would see an object of a boy in the street with a ball as a very vague, nondescript object. But a 4 gigahertz bandwidth sensor centered at 79 gigahertz would see greater detail, much greater detail. In this case, be able to resolve both the object of the boy and the ball, and maybe even guide the classification of these objects into the boy and the ball, which may help guide the vehicle to take the appropriate action to keep everyone safe. All right, so as technology moves forward, the way we're testing these radar sensors continues to evolve as well. And when we think about an ADAS system, the testing of the system is actually pretty straightforward. You test the electronics and validate the quality and the characteristics of the electronics as well as the mechanical system. And then you need to test the software that's going to run on that radar sensor or a companion ADAS ECU that will be making decisions about whether or not to actuate the brakes if it's used for emergency braking, or if that radar sensor is being used for adaptive cruise control, it would be actuating the brakes and the accelerator on the vehicle. So these systems, as they're built in a laboratory or on a factory floor, the radar sensor is put inside a chamber, a big box that's probably the size of a refrigerator, a big refrigerator or a small refrigerator perhaps. And inside that box, along with the radar sensor itself, is what's called a millimeter wave head, something that can sense the radar's signal that's being broadcast, bring that in, and then manipulate that signal and send it back out. And in that step of manipulating the signal, we can add things like objects, add things like a vehicle on the road moving at a particular speed. The objects can vary in size, the objects can vary in speed, and they can vary in location. And you can imagine, if you are a tier 1 supplier, and I think some of the people in attendance today are, if you are designing and manufacturing a radar sensor, you'll go through a few tests on the factory floor to determine that you have manufactured that radar sensor correctly. You may look for a variety of objects at different distances, perhaps moving at different speeds, and then ensure that the radar sensor is reacting appropriately to the objects that it sees. Now, if you're in validation and trying to validate the design of that radar sensor, you have to put it through many, many more testing scenarios. And here's some examples of the types of tests that have been put together by organizations like the European NCAP to give guidance to tier 1 suppliers and OEMs on the type of testing they should be doing to ensure that their automatic emergency braking system will operate correctly and be able to address the common use cases. Now, you can see here, it looks like a lot of different testing has to be done. And that's true. It is a lot of different testing, especially when you start adding different speeds and different vehicle sizes, maybe different pedestrian counts. And as you go through the matrix of tests of these different scenarios here, along with different speeds and different vehicle types on the road, you'll have a matrix of tests that's relatively large, but it's pretty quantifiable. You can get your arms around it. You can actually build a test plan that you and your test team can execute. You would again load up that test software on the test system. Your radar sensor would be inside the chamber, it's called an anechoic chamber, along with the millimeter wave head, and you would trick the radar sensor to think it's in the car, and in front of it is a vehicle, and that vehicle is changing lanes, whether it's cutting in front, or it's moving to the side, or perhaps the vehicle would think it is changing lanes, and it's moving from one lane to another, either to a lane that has a vehicle occupying the lane, such as driver cut in, or maybe moving to a lane which has no other vehicle, such as driver cut out. Okay, we'd run through all of these scenarios. We would perhaps have to manipulate the software if we find issues and correct it before that radar sensor is ready to be delivered to the OEM and designed into the vehicle and ultimately make its way on the road. Now, as long as we're dealing with an individual sensor that's driving an individual ADAS capability, the testing is relatively straightforward and bound. But as we start to go to more complicated forms of autonomy, such as things like automated highway driving, which were found in GM's Super Cruise or Audi's traffic jam mode, you're having to pull together information from multiple sensors. And then based on that information, make a decision for what the vehicle should do. So not only do you have to test the individual sensors, electronics and software, like we just saw in the previous example. You have to do that for every sensor that's included in the system. You also need to test the software that's going to be governing all those sensors involved in the ADAS or autonomous control of the vehicle. And you'll test all of those individually, and then you'll bring them all together and test them in a laboratory environment, simulating and emulating the world around the vehicle to ensure that it operates correctly across the most important use cases. And ultimately, you have to make a decision, have we covered enough use cases to be confident that our sensor and our systems will be safe on the road? This, every time we add a new sensor and every time we add a new autonomous capability, we are effectively multiplying the test cases together, which means the number of test cases begins to explode into a very large number. And because the world around us is an analog world, the number of variants that we can build around these scenarios is literally infinite, which means that the potential test space is infinite. And we know we can't do infinite testing, because if that was what we needed to do, we would never have autonomous vehicles. So we have to figure out a way to address this testing challenge. Okay, so illustrating that here, not only do you have to do the hardware validation and the software validation for each individual sensor, then you start getting into other testing scenarios where you're testing the system, you're doing more simulation, and you're including a fair amount of track and open road testing to ensure that you have the information you need for playback in the lab, as well as real world testing scenarios that it gives you the confidence that things will be safe. All right, and an additional complexity here, which oftentimes gets overlooked, is if we look at vehicles that are on the road today, that you are driving and own, and I drive and own, the ADAS systems in these vehicles are typically governed by a single sensor with a single software stack. And that functionality can be tested in a more contained way. As we look towards level 3, level 4, and level 5 autonomy, there are two emerging architectures that are becoming common. You have the completely centralized supercomputer in the car that will handle all the autonomous sensor analysis and controls decisions. That's written up here as the raw sensor data centralized processing option, the top right. And the other is this hybrid approach, where there's some software in the sensors that's taking the raw data and manipulating it perhaps into an object list, or just processing what's coming off of the camera sensor into an image that can be passed over a digital communication network or bus back to one or more processing systems. Now, everywhere you see a blue box on this visual, that's software. That's software running, which means that that software needs to be tested on its own, but you also need to bring the whole system together and test that software together as well. And thus, we end up with a pretty complicated testing challenge. And to layer on one more piece of complexity, much of the software that's being included in these centralized supercomputers are using artificial intelligence techniques and deep neural networks and other approaches that are not completely deterministic, they are probabilistic, which means that there is a probability that they will detect something as a human or as some other object, which means that having a very deterministic A, then B, then C test plan becomes more challenging because the algorithm itself has a, we'll say, fluid state of determining what it's looking at, what it's seeing, and what decision it's going to make. So to summarize all that, there are these trends, right? There's the evolving vehicle architecture, where there'll be software with each sensor, or will we have centralized processing for the vehicle, or will we have both? Also, there's organizations like European NCAP that are helping to guide automotive suppliers on what it takes to get the highest safety rating. That's great. But then there's also potentials that governments will get involved and begin to guide vehicle providers on exactly what they need to do to test their systems and ensure that they're safe. And the vehicle, which for 100 years was mostly a mechanical device, is becoming more and more software focused, which is causing automotive companies to really build new capabilities, new talent, and new skills within their organizations. And this element of deep learning, deep neural networks, and artificial intelligence is completely new to many of the test teams out there that are testing these components and testing these systems that are going into the car. So all of that's leading to increased complexity, continually changing requirements as the types of features we want to add into the car get increased, as well as the sensors themselves that are ingredients to these features continue to evolve. Cameras get higher resolution, radar sensors become higher bandwidth. All of these changing requirements cause a continual evolution of test equipment needs. And we all know that there were aspirations for having autonomous vehicles broadly deployed this year. Many companies made projections that in 2020 will be the year of the autonomous vehicle, will be there. Some actually predicted a year earlier than that, and a couple said we'll be here in 2021. But that type of visionary vision casting of what a company wants to accomplish drives down into the organization into schedules that are unrealistic to achieve. And then there's also this piece of not only are we doing electrical testing and functional testing, we need to include more and more simulation to cover the massive number of testing scenarios and test cases that these vehicles are going to require to, again, ensure that they're safe. So in practice, what these systems look like today and what the flows look like today is there's really two parallel flows. On the bottom, you can see electronics testing, where inside validation, you will run through a wide range of electrical validation tests, initially at the very low level between components, then you'll get to more of a functional level and ensure that all the electronics are working correctly. And then you do a subset of that testing, oftentimes at room temperature as well as high temperature on the production floor to ensure that what you're manufacturing is actually coming out as a high quality device, and you'll be able to put it in the vehicle with confidence and know that it's going to run reliably. On top here, we have software testing of an ADAS and autonomous system. And there's a blend of simulation testing in the cloud. And when I say in the cloud, I'm not necessarily talking to the implementation of a private cloud being hosted by one of the big cloud providers. This could also be an on-premise cloud that's owned and managed by your organization's own IT people. Both of those are included in the cloud step there. But then also for training and testing, automotive companies are doing more in-vehicle recording. It's not a new concept, but it's becoming an increasingly popular approach to getting data for training and testing autonomous systems. And that data needs to be played back as open loop testers to your ECU to ensure that your ECU is reacting as you expect. And then there's oftentimes this playback evolves into a hardware in the loop system, which uses a mix of playback and simulation data so you can put your production software running on your production ECU through a wide range of scenarios. So companies that are having the most success at advancing towards commercially available autonomous vehicles are doing all three of these testing approaches. They're doing simulation in the cloud. They're doing laboratory testing, which includes playback of road data, as well as hardware in the loop data, hardware in the loop testing, excuse me, as well as testing the vehicle on the road or on the track and acquiring road data to reuse in the cloud and reuse back in the lab. So this is a recursive process here. As we continue to evolve the design, we get it back on the road, we get more data. We use that data to test and train and onward and onward until we're confident that we've achieved our goals. And if we look at the number of scenarios that are being tested, the large share of those scenarios are being done in simulation and in the cloud because it's much easier and the scalability is much better to run these tests in simulation. And there's many things you just can't do in the lab or on the road reliably. It's hard to make it rain when you want it to rain. It's hard to get the sun exactly where you want it when you're driving on the road. But in simulation, that's power that you have. You also can simulate things like different vehicle dynamics, different weights of vehicles. So just the amount of control you have in simulation is significantly higher than what you have on the road and even in the lab. But that doesn't mean that people are investing more time and resources necessarily in the cloud than they are in the lab or in the road. It's just the number of scenarios that end up getting tested in those locations. And what is the software that's being tested? It's very similar to the explanation that we got in the prior talk. It's software around perception, which perception in this case is painting the picture of the world around the car. What are we seeing in terms of objects and the road itself, using all the sensor information around the vehicle. Then we have to do planning. We have to make a decision of what we're going to do. Are we going to actually choose this lane or that lane? Are we going to, what speed should we be at before we make our turn? And really control that driving behavior of the vehicle and the plan of how we're going to get from where we are to where we want to be safely. And then there's the controls, the actual steering and braking and acceleration of the vehicle. The controls is the easiest part. Controlling the vehicle and doing things like drive-by-wire, that's stuff that's well understood and can be handled quite easily by automotive suppliers and OEMs designing cars. Planning is relatively straightforward, but there's a lot of opportunity to add value there. But perception is the real challenge. Ensuring that your vehicle can reliably predict all the objects around the vehicle, as well as exactly what they are and characterize them and determine the free space available to drive. That's the real challenging part of this whole process. Okay, so I talked about record and replay, pure simulation, and HIL. I think they're pretty they describe themselves pretty well, but I wanted to walk through the pros and cons of each. So the reason people are doing record and replay is recording real road data with the real sensors that you're going to have in your production vehicle gives you the highest fidelity data. It's exactly what your software is going to see when it's on the road and the car is attempting to drive. It's but it's very expensive to capture the data and to annotate the data to make sure that your computer systems understand what they're seeing. To understand that a tree is a tree and a car is a car, someone has to go through and label and annotate that data. Now, in pure simulation, the fidelity continues to improve, but it's not as high fidelity as recorded data. But you have ultimate flexibility to do things that you just can't do on the road or on the test track or in the lab without simulation. And HIL is kind of the best of both worlds. You have simulation and playback data involved, and you're actually running your production software on your real ECU. So you can validate timing and behavior of the system while you're running it through scenarios. And you really can't shortcut any one of these steps. You need to do all of them, at least with the technology we have today, to reliably and confidently test your vehicle software. Now, I want to dive into record and replay for just a moment. So how a record system looks in the vehicle is in the trunk, there's extremely high performance measurement equipment that's added in line with the vehicle sensors themselves. So the radar sensors, the camera, the LiDAR, the vehicle network, the inertial measurement unit, the V2X information, the GPS information is all flowed through this instrumentation computer in the trunk of the car and then passed on to the ADAS ECU or autonomy ECU to make real-time decisions in the vehicle, as well as information is shared to someone in the cockpit that may be doing real-time annotation and note-taking of the different scenarios that you're seeing on the road. Now, systems today are acquiring data continually of roughly 4 gigabytes a second. And if you're driving the car for 6, 7, 8 hours, you get to terabytes and then very quickly to petabytes of data that you need to analyze and use in your training and testing process. And we have begun working with many companies in this space. And over the past 12 years or so, we've been helping companies verify their designs, record data, and do testing for ADAS systems. Things like backup cameras and parking systems and those types of technologies. And in recent years, we've begun to do more and more of full autonomy record systems. The system physically looks like the system on the lower right. That system has a couple of cameras, a LiDAR, and a radar system sensor coming in to the high-end instrumentation platform, which is called PXI. That's an industry standard platform for this type of system. But the record system has to be able to synchronize not only the sensor data, but also communication data from V2X, positioning data that's coming into the vehicle network data itself. And if that is not tightly synchronized, if you try to play it back in the lab or use it in simulation, it's just junk. You'll have objects in different locations at a given time if everything isn't tightly synchronized. Okay. So because of the massive scale of the data that's acquired in these systems, it makes a great deal of sense to partner with a cloud provider as well as leaders in the IT space. So we did some collaboration or continuing to do some collaboration with AWS as well as Dell EMC on data storage and data recovery, as well as on-prem in-lab hot storage using the on-premise storage technology that Dell provides. And that hot data, the data that the tester needs to use, is served up in near real time to the hardware in the loop system so they can rapidly iterate through a wide range of tests. And then all the additional data is available up there in the cloud for additional testing needs. Now, let's take a look at simulation itself and make the point of why simulation is so important. Simulation is incredibly important because you can go through a wide range of scenarios, but it's important to realize that not one simulation company has got every aspect of the vehicle and the perception stack and sensors completely covered. Today, most companies need to do some form of co-simulation. Perhaps you would use IPG CarMaker for vehicle dynamics along with monodrive's tools for the perception stack. It's just one example. And to show the variability that you get with a perception simulation system like the monodrive tools, here we're going to run through a very simple emergency braking scenario. This emergency braking scenario can be done within the rain. It can be done with different lighting conditions. Multiple sensors can be added if needed to the system. And different scenarios can be added as well that actually lead to failure mode in this case, where we had additional initial speed, which leads to a collision. And that's the importance of having vehicle dynamics in this simulation as well, because you need to know how quickly your vehicle will brake in these different scenarios. And now here's a couple of crazy scenarios, cut-in scenario, and this last one, it looks like the driver is maybe texting while they're driving or something. Pretty unreliable driver here, almost hits the guardrail, pretty extreme situation. All right, but it would be very difficult to create all of those situations on the public roads or on your test track. So simulation is absolutely key. Now, as we begin to simulate large scenarios, like an entire city or entire town, companies that are looking to roll out robo-taxis are going to want to understand the behavior of their robo-taxi systems in a geofenced area like a city or a neighborhood. The amount of data required for the mapping and simulation of a very large space gets into the petabyte range. There again, we have the need to partner with cloud providers as well as IT providers like AWS and Dell as we do these very complex, large simulations. And we work together to create a supercomputer test bed where we're testing out what's possible, working with monodrive and Dell and AWS to really learn about capabilities and how we should approach these problems. Okay, so I want to move away from the autonomy stack and actually say a few words about V2X, which we heard a great talk about V2X and the role that it's going to play from the prior presenter. And I'll just dive right into that. So one of the areas that we struggled with is there have been competing standards. There was DSRC, and now there's CV2X. CV2X appears, at least in certain regions of the world, to be the clear winner and will likely become the standard V2X communication approach. It's based on the 3GPP standard, so it's aligned with 5G. The 5G technology that will be used for backhaul of data, as well as our mobile phones and mobile devices. So combining these approaches and technologies will give us a great deal of efficiency. And we are here. We're after release 14, and we're approaching release 16 of the 5G standard, which adds a lot of new features for low latency communication. Now, it's important to remember that the 3GPP protocol is like our ears and our mouth. We're able to talk and we're able to hear, but we won't necessarily be able to understand. There you need an application layer on top of CV2X, and there's competing, or we'll say alternate communication standards for different regions around the world. And that's quite likely the way the industry will remain. We'll quite likely have multiple application layers that automotive companies need to support as their vehicles are moved from region to region, which again introduces a whole additional testing challenge in the testing matrix for sure. Now, just like with automatic emergency braking systems, V2X has what are called day one scenarios. Scenarios that we want to test, similar to the merging scenario that we saw in the last talk, are things like automatic emergency braking, left turn assist, as well as the approach of a first responder. These are the types of scenarios that need to be tested and ensure that the V2X system is responding well. Now, similar to the technology that's used for record, playback, and HIL, the same technology can be used for doing RF measurements for V2X systems, as well as doing basic application layer communication testing to ensure that you're able to understand the packets that are being sent from your V2X controller in your car, and it understands the packets that you're sending. But you could also put it through scenarios by bringing simulation into the game again, where the picture on the left is including vehicle dynamics with V2X to do things like an emergency braking scenario where a vehicle in front of the other has engaged its brakes, and then that gets communicated to a vehicle 1 or 2 or 3 cars behind so we can start to decelerate to prevent a rear-end collision. And of course, it can be extended to start to bring in sensors plus V2X into your testing. So you'll know, okay, can my radar sensor that's doing emergency braking along with my V2X, are they properly playing together and working well with my centralized controller, and all of the timing and the decisions are being done correctly for a wide range of scenarios. Okay. One last comment is I'd like to talk about millimeter wave. Now, some of you may have heard about 5G and may have heard about millimeter wave. Many of you probably have not. But I wanted to take this as an opportunity to share yet another emerging challenge that's a little bit in the future. So millimeter wave communication is in communication bands above 24 gigahertz. It's in between 24 and 100 gigahertz is commonly referred to the millimeter wave bands. And universities and researchers such as the University of Warwick, WMG, have begun exploring what's possible with millimeter wave. They have set up systems that allow them to do over-the-air communication between transmit and receive across 24 to 33 gigahertz. And they've shown an over-the-air throughput of 2.87 gigabits per second. That's screaming fast for over-the-air communication. But the challenge with millimeter wave is as the wavelengths get smaller and smaller, the communication stream becomes more and more directional. And which means that the antenna array needs to be pointing at the thing it's talking to. And lo and behold, cars move. They move around. Also, while the antennas are getting smaller and smaller because the wavelengths are getting smaller and smaller, these shorter wavelengths get disrupted by the materials that we commonly use to make cars. And most automotive providers don't want ugly antennas on top of the vehicle. They want to conceal the antennas within the vehicle. So not only have they tested what's possible from a throughput perspective, they've also begun to look at the effects of different materials at different wavelengths to understand how the millimeter wave communication gets attenuated as it's passing through the body of the vehicle or the headlight of the vehicle or the bumper, as well as how is that waveform getting distorted by looking at its delay spread. which ultimately will help govern what type of communication is possible. And I think there's a challenge to all of us to see if we can identify that killer app, that killer application for millimeter wave 5G in the car. It's the type of thing that I'd really like to talk to anybody about one-on-one or in a group setting. And if we were doing this in person, I'd definitely be seeking people out to have that conversation. If those of you are really into IEEE papers, this is a good one. It's out of the WMG. The senior researcher there is Dr. Higgins, and Eric Kempert and Dr. Jennings, who did a bulk of the work under his leadership. All right, so in summary, a lot of challenges in testing and ensuring these vehicles are safe, and that's one of the reasons it's taking us a little bit longer than we thought to get these vehicles out on the road. But we're doing our part to help test the sensors and the systems that are being critical for autonomous vehicles. And in preparation for this talk, I actually wrote an article and posted it to LinkedIn. The article is entitled 2020, the year of the autonomous vehicle, where are they? And it really covers in slightly more depth many of the challenges I've outlined today. So I encourage you to take a look. My LinkedIn and Twitter handle are both Jamie Smith and I. You tell me what you thought. If you think it was helpful, let me know. If you think it's off base, love to hear that too. Love to have a good discourse on this topic. And with that, I think I have maybe 5 minutes for questions.
Hello. Yeah, thank you very much for the session. For the Q&A, I will of course now hand over the questions that we got. So one question, actually the latest that we got, I think in connection to the radar and to the wave radar you talked about, we got the question: what sensor setup do you see most promising going forward?
Okay, so what sensor setup do I see most promising for autonomous vehicles, I would assume?
Yes.
Yeah, I would say that's a dangerous for me to take a stance on that. I think that the tier ones and the OEMs in the robotaxi vehicle fleet management people need to make that determination. We're trying to position ourselves to be able to help test. I'm going to start my video so people can see my face. I think it's up to those organizations to make the determination of what the right sensor mix is. But to do a truly safe system, redundancy is important. So if there's a failure mode due to fog or failure mode due to reflection from the sun, that needs to be mitigated. And that can be mitigated with V2X, and that can be mitigated by having a family of sensors that can cover some of these corner cases, or maybe not so corner cases, where a particular sensor won't be helpful.
Thank you. The next question that we got is, in what direction do you see testing evolve? How could costs be further lowered? I think that the cost part was also to the real life testing on the slide earlier, but yeah, of course.
Yeah, so I think without a doubt, the way to keep testing costs in check is more and more simulation, right? Because the testing space is literally infinite. To get the test coverage we need, we have to use simulation. And then we'll likely have to use some form of advanced analytics to determine what test cases actually need to be covered. So likely there'll be artificial intelligence used to guide the testing cases that actually are simulated, tested in the lab, and tested on the road.
A quick follow-up question on that. So right now, I would say as of right now, like it's more or less a mixture because of course every kind of testing has its pros and cons, like you elaborated on earlier. But do you think that with simulation, like simulating testing, you can basically cover enough that you would say it's enough to say that it's a safe way to move forward with handing out autonomous vehicles?
Well, not with the technology we have today.
Okay.
I think that the fidelity and the real-time accuracy of the simulators today is not good enough. Now, in the future, you know, I don't want to put a date on it, but we'll say many, many, many years in the future, I think absolutely it's possible that the simulators will be higher fidelity than the cameras that are actually going to be seeing what the simulator is providing. The timing will be better than what's needed for the supercomputer in the vehicle. So it's possible, but we are, I would say we're at least a decade away from that, and probably multiple decades away from pure simulation being the testing approach.
Okay. One last question, because our next speaker is already there. So one last question, but of course, now the little information as well as before, feel free to reach out to Mr. Smith, either through the LinkedIn, what you showed earlier with the very interesting article, or by email, or through our web app. Of course, I think he is very happy to receive your questions. And what my last question would be, how confident are you that the industry will be able to deliver safe autonomous vehicles then in the future, or right now?
So I'm very confident that we're going to get there. And I think it's years, not decades. I've heard some people answer the question, it's the minute we hit the singularity, the minute the vehicle is as smart as the human. And I don't think that's going to be required. I think we're making progress, and we're getting there. So I think it's years, not decades. And I have the utmost confidence in the engineering talent that's working on this problem across a wide range of suppliers and OEMs and technology companies. And it could be next year, it could be 5 years from now, or maybe somewhere in between.
One last question that I actually got that I nevertheless want to give you. It's just a really short one, but I'm actually also very curious about your answer. Do you think in regards to years, not decades and so on, what impact do you think has the current crisis, if that is something you can actually foresee? Because of course it's,
Yeah, I say a few words on that in the article. I think it delayed things. You know, I think that is it really just going to be delaying everything for shutdown, which happened for most of us in mid-March, to vaccine, and just everything's going to be pushed out that period of time? Maybe. It's probably not quite that. It'll probably be about 60% that time, but things just got slow because everyone's got to rethink what we're doing. Because that lab testing we were talking about, no one can go to the labs, right? And if you have a safety driver and somebody in the car annotating, they're not 6 feet apart. They can't be in that car together, so they can't social distance. So it's just people have to rethink how they do these things until we have the vaccine. So it's just delaying things, but it's not going to be catastrophic by any means.
Well, yeah, I would say with those optimistic and warming words, thank you very much, Mr. Smith, for the presentation and the inputs. Of course, like I said, feel free to reach out to him through the multiple options laid out earlier. And yeah, thank you very much. I will now